Hello and welcome to our latest Pick Gardener web seminar. Today we'll be talking about solutions for cosmetics all around color, appearance, and dispersion. My name is John Kowalski. I'm part of the marketing team here and will help facilitate this. We are recording this and tomorrow during a follow-up email we'll send you that recording link along with the presentation materials. Also, if you have any questions, please use the Q&A box located in the bottom right-hand corner of your screen, and time permitting, we'll get to them. If we do run out of time, we'll follow up with you individually to get your question answered or respond to your comments. So with that, let me introduce Mr. Corey Cohen. He is our Senior Application Specialist and our presenter for today. So with that, Corey, it's all yours, sir.
Thank you, John, and good afternoon, everybody. As John mentioned, the focus of today's web seminar is on cosmetic solutions. We're going to begin with talking about measurement of color and appearance in order to QC the look of cosmetics, and then we'll finish with a brief presentation on dispersion. So during the first part of today's web seminar, we're going to begin by talking about measurement theory, various kinds of measurement, beginning with the theory behind color measurement, just a real quick overview of both solid and metallic or sparkle pigments. We're going to talk a bit about gloss measurement and also about transparency measurement, specifically haze, clarity, and transmission or transmittance measurements. And once we've got some of the theory down, we're going to talk about some specific applications for cosmetics, things like how to measure nail polish, pastes and powders, lipsticks, artificial nails, and soft focus cosmetics. So measurement of cosmetic products, first of all, it's important because for one thing, appearance, when products look good, consumers perceive that that product is a quality product. So the appearance is very closely tied to a consumer's perception of the quality. So this is a strong factor in purchasing decisions. This is, of course, first established by the visual impression in the store. So not only does the cosmetics themselves have to look good, but so does the packaging. This has a high impact on brand loyalty, specifically things like batch-to-batch consistency. Because, of course, if you settle on a product that you like, a cosmetics product that you like, you want it to be consistent every time you go to the store to buy it. So batch-to-batch consistency for color and appearance has a high influence on consumers' perceived quality as well. So in order to achieve all this, consistent color and appearance needs an objective eye. So now again, starting with the theory. When we have solid colors, and we refer to objects as solid colors or colors of solid colors when they only have absorption pigments in them. Absorption pigments are just our normal everyday pigments that give objects their color. They selectively absorb different wavelengths of light. So for example, a blue color is going to reflect lots of the blue wavelengths and absorb most of the other wavelengths. So this is what we refer to as absorption pigments. So when we measure color, we need to have standard viewing conditions and measurement parameters, and that includes things like the illuminant. The organization CIE has standardized a number of different illuminants, which are all programmed into our spectrophotometers in order to accurately calculate what the color looks like under that illuminant. Of course, the object is what a spectrophotometer measures. It measures the spectral reflectance curve of an object, and that's just what percentage of each wavelength is reflected back by the object as opposed to being absorbed by it. And then the observer functions. This has to do with how we actually perceive colors, how our eye is built to detect different colors of light. And so those functions, the observer functions, have to be built into the spectrophotometer as well in order to accurately measure color as we see it. So you take all three of these sort of sets of numbers, the illuminant, the object, and the observer, and they can be put together to produce color scales such as XYZ, the tri-stimulus values, or LAB, which is the more commonly used system. So here we have the LAB color system. Again, this was designed by the organization CIE, and this is a three-dimensional coordinate system where you can describe any color as a position in this three-dimensional space using these three values, L, A, and D. So the L value stands for lightness. The higher the L value, the lighter the color. A and B are the chromatic axes. So the A value tells you how much red or green is in a color. If the A value is positive for a color, that indicates it has red in it. If it's negative, it indicates it has green. And of course, the higher the color, the more chromatic that color is. The higher the A value, the more chromatic the color is. Similarly, the B value stands for blue or yellow. So a positive B value indicates the presence of yellow in your color. A negative B value indicates the presence of blue. And of course, the higher the B value or the more negative the B value, the more chromatic that color is. And so when we measure color, typically what we're concerned with is not the absolute values of the color. We want to know how closely one color matches to another color that we typically refer to as our standard. The standard is the target color. That's what you're aiming for. And so you'll have a target color, a standard color you're trying to match, and you want to know how closely your production colors match that standard. And so you'll measure the LAB values of your standard or your target. You'll measure the LAB values of your production color, and then you'll plug it into this equation here, this delta E equation at the bottom to get the overall color difference. And that involves calculating the difference in the L value, the difference in the A value, the difference in the B value, square them each, add them together, and then square root it to get the delta E value. And so the delta E value here is really just the distance between two colors in this LAB color space. So if you were to plot two colors in this space, two sets of LAB values, and just measure the distance between them, that's actually what the delta E value is. And that's just a single number that tells you how far apart these two colors are. So the higher that delta E value, the further apart or the worse match these two colors are. So delta E, the equation we saw in the previous slide, we refer to that as delta E star, and that's the simplest form of the color difference equation, but it's somewhat flawed for certain reasons that are illustrated here in this graphic, this color wheel that you're seeing here. The idea with this graphic is that each of these shapes, these little circular or elliptical shapes, that's what we call a tolerance shape. And so in the center of each shape is a standard or a target color, and any other color existing inside that shape would be indistinguishable to the human eye when compared to that standard. And so we can see that as we go across this color wheel to different portions of it, these tolerance shapes take on different sizes and different shapes. Some of them are more spherical. If you go towards the center, towards the achromatic or the more neutral colors that have less chroma in them, those tolerance shapes tend to be more spherical or circular. And as you go further out, they become more elliptical, so the shape can change, and also the overall size can change depending on where we are in color space. And so the effect this has is that if we calculate a delta E value for, say, two neutral colors, two near white colors, or near gray colors or something. A delta E of, say, 1 might be very, very noticeable. That color difference might be noticeable for a neutral color, whereas if we take a very chromatic color, like one of these greens, and we compare two green colors, a delta E of 1 might not actually be distinguishable to the human eye. And so, delta E color, or C-lab color space in the delta E star equation is not perfectly uniform. And so because of that, there have been developments of more advanced color difference equations over the years, including delta E94, CMC, 2000, DIN 99. So the goal of all of these improved color difference equations is to make color space more uniform, so that a color difference of 1 for a green color looks the same as a color difference of 1 for a gray color or a red color or a purple color or whatever. And so to measure solid colors, we have our Spectro 2 guide instrument for portable color control. This is a handheld instrument. It can do both color and 60-degree gloss in one measurement. It also does fluorescence measurement if you're worried that your colors may be fluorescent, or if you need to control the fluorescence in your color, the Spectro 2 guide can quantify that fluorescence. It provides for the use of digital standards, meaning if you have a whole supply chain, or maybe you have a large production plant where you're using many of these instruments, you can actually just measure your standard with one instrument and then distribute that standard digitally to all your different instruments for measurement. And that way you're getting the most accurate measurement to your color standard possible. It uses innovative LED technology, which provides excellent repeatability and inter-instrument agreement, which is necessary to use those digital standards. The different instruments of the same type, in order to use digital standards, you need to have very, very tight agreement, and that's what you get with this LED technology in the Spectro 2 guide. It is very long-term and temperature stable, and very low maintenance, so much so that we actually guarantee the light source for 10 years from the date of purchase. So that was for solid colors. Remember, those are the absorption pigments. But when it comes to things like cosmetics, there are also specialty pigments that are sometimes used that can provide a sort of a sparkly effect. And this is due to pigments that have a mirror-like reflection, and it can cause something called light-dark flop. And that's an effect where the lightness of your object can actually change depending on the viewing angle. If you move from angle to angle, the apparent lightness can actually change, and that's called light-dark flop. And that has to do with the orientation of the flake. It has to do with several things, but largely the orientation of the flake, the type of the flake, the amount of flake, things like that. And so again, the visual perception of metallic finishes or any of these sparkly type pigments depends on the viewing geometry. And so this is why for these types of pigments, these types of materials, we like to measure these colors with a multi-angle spectrophotometer. And so here you see a typical setup, the typical geometry for a multi-angle color meter. Here we have our lamp, our light source, positioned at 45 degrees off normal. And then here we're seeing 5 different measurement angles, 15, 25, 45, 75, and 110 degrees off the specular. And the reason to measure at different angles is because of that light-dark flop. Because the lightness is going to change depending on the angle, you also need to measure the color at various angles to make sure that the colors are going to match, that your production colors will match the standard, not just at a single angle, as with solid color instruments like the Spectro 2 guide, but at multiple angles. So cosmetics often use interference, or what are called pearl pigments as well. And these pigments cause an interference of light, which can cause certain effects like a certain luster effects and color flop, where color flop is where not just the lightness and darkness, but the actual hue, the color of the material can change depending on the viewing angle. And so again, the visual perception of interference finishes, much like metallic finishes, depends on the viewing geometry. So specifically for interference pigments, where you're dealing with color flop, we added in an additional sixth measurement angle, what we call the behind the gloss angle at -15 degrees, which is often where those interference pigments tend to display that color flop effect the most. And so here we're seeing a measurement of a pearl finish, a material with interference pigments in them. This is plotted in AB color space, so we can see these are going through the different angles on this multi-angle color instrument. And so we can see how the actual color of this material is changing as you go from angle to angle. It's getting redder, redder, redder. And then this last one, this red one, is the behind the gloss angle, the -15 degree. And we can see that that's the one that's displaying that the most drastic color flop effect, where it switches way over to the other side of AB space. So in addition to color evaluation, it's necessary or desired at least to also evaluate the visual effect of those special pigments, those sparkly pigments. And so under direct illumination, like sunlight, those pigments can start to sparkle. They have sort of a brilliant sparkly effect. But under diffused illumination, where the light is sort of hitting the material at all different angles, sometimes those pigments, those sparkly pigments in the material, can cause a sort of a grainy pattern that we refer to as graininess. So the visual perception changes not only with viewing angle, but also with illumination conditions. So the goal is to develop a solution to characterize the total color impression. We need to measure color at multiple angles. The color perception changes with viewing angles, so we need multi-angle color measurement. Color perception changes with viewing conditions, so we need flake characterization. And so this is done with a camera analysis. This instrument has a CCD chip positioned normal to the surface, corresponds to the spatial resolution of the human eye. Camera pictures are taken under different lighting conditions to simulate both a sunny sky and a cloudy sky. So these, what you're seeing in this diagram here are three different illumination angles to simulate a sunny sky, and then there's also a diffuse illumination to simulate a cloudy sky for that graininess effect. And so the sparkling impression is evaluated under three illumination angles: 15 degrees, 45 degrees, and 75 degrees off the normal. And of course, in our Smart Lab software, you can evaluate your sparkle measurement using these graphs of sparkle area versus sparkle intensity. These are two values that the instrument will give you. Sparkle intensity tells us how strong the flashes of light are off of each of those individual sparkle pigments. And the sparkle area tells us how much total area is being taken up, or how much total area we can see that sparkle effect. And then there's a delta sparkle equation that takes into account both sparkle intensity and area, tell us the overall sparkle difference between two different materials. This is the instrument that does all that, our BICMAC I for portable multi-angle and effect control. This does 6-angle color measurement, including those 5 standard angles plus the behind the gloss angle to account for those interference pigments. So it can measure both light dark flop and color flop. It does sparkle and graininess analysis with that CCD camera. And it also detects fluorescent light excited in the visible range. This, again, similar to our Spectra 2 guide instrument, uses unique LED technology, provides for excellent technical performance, no lamp changes needed. Those LEDs are going to last pretty much forever. And this allows for the use of digital standards as well. So next up, we have gloss. So the visual impression of gloss is dependent on surface conditions. The more light that is reflected back directly at the opposite angle to the light source, the more obvious the impression of gloss. So here we have a very smooth surface. We have a direct illumination by this light source here to the left. So that light is bouncing off of the surface, and because this is a very smooth surface, most of that light is going to reflect off at the opposite angle, or what we refer to as the specular angle. And because of that, the surface is going to appear very glossy. And then we have over to the right, we have a surface that has lots of micro roughness, meaning that light isn't going to bounce off as neatly. So when that light source shines that light on the surface, less of that light is going to reflect off at that specular angle, the opposite angle, and more of it is going to be diffuse. It's going to reflect off at all different angles because the light is bouncing off of those little microstructures in the surface. And so this is going to appear much less glossy. So to build a gloss meter, light intensity is measured over a small range of the reflection angle. The intensity of that light, the measurement is dependent on the material and angle of illumination. And the measurement results are related to the amount of the reflected light from a black gloss standard with a defined refractive index. So a smooth black glass was defined as having a gloss value of 100 gloss units, and your gloss measurements are going to be relative to that smooth black glass. This is the standard for measuring with gloss meters. So there are 3 different standard measurement geometries for gloss according to international standards: 20 degrees, 60 degrees, or 85 degrees off the normal. These 3 are necessary to obtain clear differentiation over a complete measurement range from matte surfaces to high gloss surfaces, and they use the same source aperture but different receptor aperture. And so this graph here illustrates why we need 3 different gloss measurement angles for different gloss levels. So the idea here is that on the x-axis we have perceived gloss. So you can think of this as 13 different gloss panels, each of them equal steps in gloss difference. So the visual gloss difference between panel 1 and 2 is the same as the visual gloss difference between panels 6 and 7, is the same as the visual gloss difference between 12 and 13. So each of these are equal visual steps increasing in gloss. That's on the x-axis, and then the y-axis we have measured gloss values. So we can see measurements of each of these panels as taken with each of these 3 measurement geometries. And you can see that even though these panels are linear, the gloss differences are linear visually, they're not so much linear when we measure the gloss values. And so we can see that, for example, if we want to measure the difference between the 2 and the 3 gloss panel, if we measure that with our 60-degree meter, we're only getting a difference of 1 or 2 gloss units here. Whereas if we measure the difference between, say, the 7 and the 8 panel, we're getting something like 16 or 18 gloss units difference, even though visually the difference between the 2 and the 3 is visually the same as the difference between the 7 and the 8. So this is why we have different gloss geometries, and you always want to use the gloss geometry where the measurement curve is going to be nice and smooth and have a nice steep slope. And so we can see that for the 60-degree geometry, that's between about the 5 and the 9 panel, between about 10 and 70 gloss units. For the 85-degree geometry, that curve is mostly linear in the low gloss range. And then for the 20-degree measurement geometry, that curve is more linear in the high gloss range. So we have different gloss geometries depending on what gloss range you're measuring in. So the general convention that we recommend is that if you measure your surface and get a gloss reading of between 10 and 70 gloss units, if you measure the surface with a 60-degree gloss meter, I should say, and get between 10 and 70 gloss units, you should stick with the 60-degree geometry. If you get greater than 70 units with that 60-degree meter, then you would want to switch to the high gloss meter, the 20-degree geometry. And if you get less than 10 gloss units, you would want to switch to the 85-degree geometry. So our solution for gloss is called the microgloss. It is an industry standard, a very well-known, well-established gloss meter. You can buy them in single angle or all 3 angles in one. You can take just one measurement and get gloss values at 20, 60, and 85 degrees in 1 meter. It does an automatic calibration check in the holder. And we have various measurement modes depending on your task. It can do statistics, difference mode, pass fail, if you input tolerances. It can also do online measurements or averaging if you're measuring a large surface area. Okay, so next we're going to talk about transparency measurement. Now, when it comes to transparent materials, if you want to know sort of how the light is going to pass through it, how clear an image will look when looking through a transparent material, you might want to measure the haze and the clarity. Haze deals with wide angle scattering, and clarity deals with narrow angle scattering. And so here's a visual that sort of tells you what the difference is between the two. On the left, we have a material that's exhibiting wide angle scattering. So we would say that this is a hazy surface, and you can see that it's not really causing any fuzziness, but it's more a reduction of contrast here. And the image that you see through a material like this is going to be sort of independent from the distance of the object from that material. Whereas if we look at clarity over to the right, this is narrow angle scattering. So this is a material that's causing scattering of the light as it passes through at very narrow angles. And this is going to cause more of a fuzzing of the edges than with haze, and also the distance of the object from this material is going to affect how clearly we see it. Anything that's closer up, we'll see more clearly. As the object gets further away from our window or whatever we're looking through, it's going to get fuzzier and fuzzier when we're talking about low clarity materials. So to measure this, there are 3 measurement principles in this instrument. The first one is called total transmittance. And this is just a measure of how much light is passing through this material relative to open air. So it's calibrated to open air. Open air is considered 100% transmittance. And then you put your sample in front of the port and measure how much total light is passing through that sample relative to open air. And that is expressed as a transmittance percentage. Now for haze, what we want to do is isolate the diffuse transmittance. This is a light that's passing through the material, but is being diffused towards wide angles, as opposed to passing straight through. So when measuring the diffuse transmittance as opposed to the total transmittance, a light trap is opened up that just swallows up that directly transmitted light, the light that passes straight through, and removes that from the calculation. So in this case, only the The scattered light, the diffusely transmitted light is measured, and then the haze value is calculated as the ratio of the diffusely transmitted light to the total transmitted light. Now for clarity, remember we're only concerned with narrowly scattered light with clarity, and so we're only measuring the light transmitted at very narrow angles off that center axis. And so for this we have two sensors, a ring sensor and a center sensor. The clarity value has to do with the ratio between the amount of light collected by these two sensors, specifically the difference over the sum. So the instrument that measures this is called the Haze Guard Eye. It is the industry standard for measuring transparency. Again, you get three measurements all in one: the total transmittance, the transmission haze, and the clarity measurement. Again, this is very, very repeatable, very long-term stable due to both a reference beam to ensure that the light source stays consistent. And of course, we know that it will because it uses also our innovative LED technology, which again, we do warranty for 10 years in this instrument as well. Also has an open design for both small and large specimens. It's very easy to measure with this instrument. Simply place your material, whatever you're measuring, in front of the port and press the button. You don't need to have a big hood or enclosure in order to measure specimens, in order to measure samples. You just put it in place, and it has an open design and will still provide repeatable measurements. Also has a large touch display, a color touch display for onboard analysis, versatile sample holders for films and sheets, and also for cosmetics. So now that we've discussed some of the measurement principles that you might use to measure certain materials, we can get into exactly how you might use these instruments to measure your cosmetics. So some prerequisites for repeatable results: standardized sample preparation. This is very, very important. You always want to prepare your samples in the same way in order to get consistent measurements. Otherwise, if the sample preparation is not consistent, you might get variations in the measurement that don't reflect actual variations in the material. You generally want a smooth sample surface for measurement, smooth and homogeneous. So some challenges specifically when it comes to cosmetic products. They are often liquid, they can be sticky, they can be powdery. This makes them difficult to handle and difficult to prepare the samples in a repeatable way. So we have some solutions, some accessories for these instruments I've gone over in order to prepare the sample in a repeatable way to get accurate, repeatable results. So when you're dealing with liquids, you want to have repeatable drawdowns in order to measure your material in drawdown form. In order to do that, you need a couple things. You need charts, a substrate, a consistent substrate to draw your material down on. So this is why we have our BICO charts, which are consistent in both color and gloss, so that you know that you'll get consistent results from batch to batch. You want to have uniform film thickness, particularly when you're dealing with materials that aren't necessarily fully opaque. It's very, very important that when you draw down these materials for testing, that you get a uniform film thickness. And so you can use wire bars or wire wound rods, as they're called, for uniform application and good pigment orientation. And you can also use an automatic film applicator. This is because drawdowns done by hand can vary depending on the operator. Different operators use different speed and pressure when drawing them down, and that can cause differences in the drawdown that will lead to differences in the measurement results when, again, that might not actually reflect on the material itself. So automatic film applicators are recommended so that you get a consistent drawdown every time. You can also use the choice of wire bar depends on the mean particle size, and you want to select the wire bar closest to the mean particle size. Measurement of pasty products. These are things that are very, very viscous products, sort of liquidy, but don't flow. Some examples of this might be lipstick paste or creamy eyeshadow. And so the challenge with these types of materials is to avoid contaminating the optics of whatever instrument you're using to measure them. And so for that, we have what we call the sample holder round dish. These are small dishes that you can fill with your pasty or powdery product and then place in this apparatus for measurement. Now, each of these sample holders for the round dish comes with a template or a mask that goes over top of it, and we have various masks fitted specifically for each of our instruments. We have one for our gloss meters, we have one for our Pigment meter, the multi-angle meter. We also have one for both the current generation Spectra 2 guide and our previous generation Spectra guide models. And so what this does is when you put your material in this dish and flatten out the top and then put this mask over it, it provides for accurate, consistent, uniform measurement without risking contaminating the aperture of your instrument with the product that you're measuring. So to prepare your samples for repeatable and reproducible results, you always want to use the same amount of the product in the dish. You want to make sure the surface is, again, smooth and homogeneous. Oops. And that was it. So yes, you always want to make sure that you're being very consistent with your sample preparation so that from measurement to measurement, you're always comparing apples to apples, always taking the same type of measurement so that they're comparable with each other. And any measured differences you get will be actual differences and not due to the sample preparation. So for measurement of lipstick paste, sample preparation for repeatable and reproducible results includes heating the paste in a water bath to decrease the viscosity. You want to stir for a uniform dispersion shortly before applying. Heat both the applicator and substrate plate to keep that low viscosity. If you heat a material and then put it on something cold, of course, it's going to firm up very quickly. And again, you want to use an automatic film applicator to standardize the speed and pressure of the drawdown for more consistent results than doing them by hand. So after doing your drawdown, you can place your wet drawdown template over the drawdown without touching the surface of the wet sample. And so here are our wet drawdown templates, very similar to the masks used for the round dish sample holder, except these are designed to be placed directly onto a drawdown for measurement using, again, gloss meter, Pigment, Spectra 2 guide, or Spectra guide. That brings us to measurement of powdery products. Some examples are eyeshadow, blush, or facial powder. And again, the challenge here, similar to with pasty products, is to avoid contaminating the open optics of the instrument. And so again, we want to use the sample holder round dish for your powdery products as well. Again, we have disposable dishes for fast handling, adapter rings customizable for different cup sizes. If you have certain dishes that you already use, we can customize an adapter ring for you that will fit very nicely into this sample holder. And then again, these masks to ensure both centered positioning and to ensure that the aperture of your instrument does not get contaminated by these products. So again, for sample preparation, always use the same amount of powder. Always maintain the same plunger pressure and plunger tissue. This is for a, if you're using a press to fill the dish with your sample. And you want to choose fine woven fabric to obtain as fine pressure as possible on the surface. And that's to ensure that the surface is smooth and, again, homogeneous. So now we have measurement of small and curved products, things like lipsticks and artificial nails. So a challenge with these types of materials is, again, you don't want to contaminate the aperture of your instrument when dealing with something like lipstick. You also need to be able to cover the entire measurement area, which can be tricky when dealing with samples this small. You also want to avoid the influence of ambient light. So for that, we have what we call the sample holder cosmetics. This provides for precise and repeatable positioning of your sample. Again, we have instrument masks to ensure centered positioning and to ensure that your aperture is protected from touching any materials that might contaminate them. It also blocks out the ambient light so you get consistent repeatable measurements. And they're made of durable, easy to clean materials. So this is what the sample holder looks like on the inside. There's a little drawer that pulls out for you to put your samples into. And we have these little holders, one specifically for lipstick and one specifically for nails to ensure, fake nails, to ensure that the positioning of your sample is exactly the same each time. So again, any measured differences that you see are actual differences in the material and not just due to differences in the way they're being measured. And in addition to that, we have what we call a cylinder kit. This is specifically for measuring cylindrical objects of a certain size, mostly like spray cans, like hairspray cans. So this has more to do with packaging, but if you have a need to measure color or gloss on a can like this, we have a cylinder kit that you can customize specifically for your product. So measurement of soft focus products, this is where the transmission measurements come in. The effect of imperfections on the skin is that light is trapped in these micro crevices formed by wrinkles. Trapped light is absorbed and generates dark spots shown on the skin. And so the solution is to use specialty pigments designed to create a soft focus effect. And so this actually means that these products are going to have high total transmittance to reflect that natural skin tone, but also you want to have high diffuse transmittance to evenly distribute the light reflected from skin, hiding imperfections. And so when we're talking about high diffuse transmittance, what we really mean is that the material is going to exhibit high haze. So for soft focus materials, you want both high transmittance and high haze. So to prepare samples for soft focus products, again, you want repeatable and reproducible results. So you want particles dispersed in a basic medium You want a uniform drawdown made on either a glass plate or a crystal clear polyester film, something that something transparent that the light will easily be able to travel through, so that you're not measuring the substrate, you're actually measuring the soft focus product. And again, it's recommended to use an automatic film applicator to achieve the same speed and pressure for consistent drawdowns. So here we have different pigment types and sizes. The blue group here in this graph, we have a graph of total transmittance versus haze. This blue group is samples that are very, very translucent. This means high transmittance and also high haze. So this is good for soft focus products. It maintains a natural skin tone. The green group has very high haze, not as high transmittance, but much, much higher haze, somewhat higher haze, I should say. And that causes soft focus, but a semi-translucent effect. So this is what the haze guard eye is for measuring both the transmittance and haze to make sure that those soft focus products are going to provide the effect that you want, both the high transmittance to keep the skin tone, but also the high haze to hide those imperfections due to the diffusion of light. All right, that was it for our presentation on color and appearance measurement of cosmetics. Now I'm going to switch to our presentation on dispersion. Looks like we're running a little short on time, so I'll go through this one quickly. First of all, VMA Getzmann VMA Getzmann is the company that makes Dispermats. They're German-based. Founded in 1972 in German. BIC has exclusive distribution and service rights in both the US and Canada since 1988. They are family-owned, have over 100 employees, and produce dissolvers, bead mills, and basket mills for laboratory, pilot plant, and production. I'm going to skip past some of this. So reasons for dispersing. Dispersing provides for better wetting of particles, breakup of van der Waals forces, reduce to primary particles, improved color strength, better gloss, improved appearance, improved pigment efficiency, reduced raw materials cost, better product consistency, formulation improvement, consistent particle size. I'm going to go with distribution and better upscale results. So lots and lots of reasons to use dispersers for your products. Problems with improper dispersion of pigments include color change or poor color stability, flocculation of pigments. That's when pigments either don't break apart or come back together and form larger particle sizes than you want. Poor dispersion can cause sagging, leveling issues, I should say, settling, reduced gloss levels, or separation. Critical pigment dispersion properties are stability. Pigments require strong color fastness to reduce fading over time. Brightness, this will provide the best color. Pigment size, the rule of thumb is that smaller pigment particles provide improved transparency, better color, and reduced cost by using less pigment. And also viscosity, lower viscosity is usually better for improved particle size distribution and processing. It's important to remember particle size, this is a reduction only of particle size. You're not actually destroying the particles, you're just breaking them up into more smaller particles. Agglomerates and aggregates are reduced to primary particles. Shear forces are responsible for the separation, and additives are needed to keep primary particles in a suspended state. So here we have some various particles and what they look like under a microscope. This is a 1 micron scale here. So the dispersion process includes wetting of solid particles, mechanical breakdown of agglomerates and aggregates into primary particles, and small particle stabilization. So here again, we have the dispersion process, wetting, grinding, and then stabilization. So the type of dissolver, the type of disperser to use would depend on the approximate particle size you're aiming for. For larger particle sizes, you can use a dissolver. If you want a smaller particle size, you might consider getting a bead mill. So the dispersion process for dissolvers, there's a pre-dispersion process, and then dissolvers, and then the dispermat line SC, LC, CV, CN, and AE. For, again, finer dispersing, milling, grinding, you can use a bead mill, either a vertical bead mill, basket mill, or horizontal bead mill. So this is the calculation of the tip speed of the dispersing disc, the dissolver disc. Pi times the diameter of the disc times the RPMs, or the number of revolutions of the shaft, gives you the speed of the tip. Now, when dispersing, what you're aiming for is what we call the donut effect. And so here we have the donut effect in action. It actually looks like a donut, hence the donut effect. And that's what you're looking for when dispersing. You know that when you're getting that donut effect, you're getting the proper distribution of the material. You have a good ratio of amount of material to container size to disc size. So here's an example again of a good-looking donut effect. This is for a velocity, a tip speed velocity of 21 meters per second, and a motor power of 850 watts. And then here we have that same tip speed of 21 meters per second, or the same attempted tip speed, but here we have a lower powered motor that isn't able to keep up with it. The viscosity of the material, the liquid, of course, is going to push back on that disc as it spins. And so if there's not enough power in the motor, not enough power in the shaft, it's not going to be able to maintain the speed desired, and you're not going to get that good donut effect. So for optimizing the dispersion result, you want to consider things like the duration of dispersion, that donut effect you always want to aim for, the tip speed, geometric consideration, you want to choose the right impeller disc, the amount of mill base is a consideration, pigment and filler concentration. You want to typically disperse at as low a temperature as possible, and you need to use additives for better wetting and dispersing to prevent flocculation. So some of the differences between a dissolver and a bead mill: a dissolver has a limited energy input, it has limited shear force, it can only deagglomerate particles, there's no real breakdown to primary particles, but it's a necessary step for dispersion. In this case, color strength is limited. Bead mill has higher energy input, further deagglomeration, real breakdown to primary particles, and improves product characteristics like particle size, color strength, transparency, and particle distribution, and probably other things. So here we have a laboratory dissolver. It's a complete safety device, variable speed, max of 20,000 RPMs, large choice of accessories for different applications. I'm sure that's supposed to be explosion-proof design. Software is available for premium models, and there are models for lab, pilot, or plant.
Thanks, Corey. This is John jumping in here. And I think let's wrap it up here because we've had several webinars strictly on dispersion, and I know we just wanted to do an overview here, but I wanted to save a little bit of time for just a couple questions. You're good with that, Corey?
Sure.
Okay, and if anyone on the phone too, you'll receive this full presentation. And if you have any specific questions regarding dispersion, bead mills, color, appearance, anything that Corey covered today, don't hesitate to reach out. You can respond directly to the email, the follow-up email you'll get from marketing tomorrow, and we'll get it to the right person there. But before we end, I really wanted to answer these couple questions here. For powdery products like eyeshadows, would you suggest using the Bic Mac? Did we lose Corey?
I'm sorry, I was muted.
Sorry.
So no, Bic Mac is not necessary for most powders. Bic Mac multi-angle color measurement is really only necessary for products that use those specialty pigments in them, either those metallic type pigments that provide that sparkly effect that cause light dark flop, or the interference pigments that cause that pearl effect, that color changing effect, what we call color flop. So only materials where the appearance, the color, or the lightness is going to change from viewing angle to viewing angle. Most materials, if it only has absorption pigments in them, what we call solid colors, they're not going to display that flop effect, and so you really only need a solid color spectrophotometer, either a 45-0 or sphere instrument to measure those.
Okay. Next one from Christian here. Are the devices able to be controlled remotely? Also, does the device offer the option to capture the data through the Ethernet or serial communication so it can be stored in an external database?
Well, let's see. So for controlling remotely, we do have online measurement for most of our instruments. All of the ones that I went over today are microgloss, the Spectra 2 guide and Spectra guide. The Bic Mac all have online measurement. If you're talking about more like robotics, the actual measurements being done automatically, we do have a robotic version of our Bic Mac and also our wave scan instrument. And what was the last part of the question, John? Ethernet,
sure, it was
right.
Ethernet or serial communication stored externally.
So all of our instruments nowadays use USB communication, but using our Smart Chart software, you can download the measurements or measure in online mode and save those measurements into SQL databases.
Excellent, excellent. Dispersion question here too. For the laboratory dissolver, what's the minimum sample size needed? Is that something you know?
No idea. Anyone else on the line?
Yeah, we apologize. Corey's doing a great job filling in here, but our business line manager had to attend to some other issues, so he couldn't be on this webinar. But we can definitely, unless any of the field salespeople on the line know, Gurnish will definitely follow up with you directly. We'll get you in touch with Andy Stumer, who is the business line manager. he can help you with answering that question and anything else you may have. You're welcome, Curtis. Thank you. All right.
I think
with that,
the minimum
go ahead, Greg.
the minimum container size, I believe, is 250 milliliters.
Okay. Great. Thank
But
you.
that doesn't necessarily mean you need 250 milliliters of product, right, Greg?
Correct. You're gonna need some minimum. It's going to depend on which model you also are looking at. So there's one that goes down to 30 milliliters. So we'll follow up on a one-on-one discussion there.
Sounds good. Appreciate it, Greg. Thank you. And with that, I think we'll wrap up. Like I said, you'll receive a link tomorrow with the copies of the presentations as well as a link to the recording. At the bottom of that email, we'll have a list of scheduled webinars. We'll also be looking to expand that over the next couple of weeks to fill out the remainder of the year. So too, if there's something you have in mind that you need some assistance with or you think would be a good topic that we should cover that would benefit many, feel free to respond to the marketing email you get tomorrow, and we'll see if we can work that into the schedule too. So with that, thank you, Corey. We really appreciate your expertise and time. Thank you, everybody, for attending. Hope you learned something, and we look forward to seeing you on a future Vic Gardner web seminar. Thank you.